right, everybody. So yesterday we made 4 node objects, N1 through N4. They were generic data, so we made them hold strings, and we wrote 4 different constructors. So when you make a node, we gave it options. And we can see that right here from where it's called. So in N1, you make a node with a default constructor saying it's just a node. Don't worry about what the data is. Second one, we said, oh, well, here, this is what the data is. It's going to be the letter B because we use strings. Okay? For node 3, I said, well, yeah, it's going to hold a C, but as well, node 3 is linked to node 1. It will be the next node that it's linked to. And in node 4, it holds a D, and N2 and N3 are the 2 nodes it links to. One is the next node, the other is the previous node. And we can see that in the node class that we wrote. Okay, so in this node class, you can see again right here, these are its properties. These are the constructors, the ones we just talked about. And we did this neat feature where we used the word this, so that basically all these 3 constructors call the other constructor. And I just showed you guys that as a way that you can kind of centralize your code and shorten it up a little bit. Okay, so here's what I'm going to start today with. We made our 3 properties public. Did we have to? What were our other options? Private. And what else did you learn? Protected from the last unit. And if we do that, if we make them either of these, we enforce encapsulation. That idea that we don't need to see these outside the class. Would that be possible in this class? Sure it would. We could make them private. If we did that, the only way we could change the data or access the data would to write a method like set or get. Who remembers the fancy name for those 2 types of methods? And mutators. Excellent work, kids. That's right. Accessors and mutators. But in this case, I think that's not necessary if we just make them public, because if we think about it, the node class is never actually used, although we did it in our test. The idea is, and this is just our sort of work from before, the idea is that we're going to be using the linked list class. That's the class we're going to actually be using and its methods. But hidden inside here will be the node class. The node class is used by the linked list class. So it's like we're not really going to be using the node. So it's okay that things are public. That would be an argument. But there would be nothing wrong with making mutators and accessors for this class. Just trying to shorten our timeline here a little bit. And I don't think it's necessary. Okay. So in addition to those methods, we have a couple other ones that our template brought in. One of them is the toString method. That would be useful so we could actually see these nodes. So the way we wrote it in our template was it goes to the superclass and turns it into a string. So I wonder how that would work if we outputted these nodes. So let's go to our tester class and let's output node 1. So let's S out N1. Now, by doing that, it'll turn N1 into a string. We could also call it by going dot to string if we wanted to, but that's done automatically every time we print it. And I'm going to do that with all 4. So N1, 2, 3, 4. And let's run this. Let's see what this method, super.toString, will do with it when it outputs it. Well, here's what comes out. Collections.node at 2A139A5, collections.node at 15. What is this? This looks like garbage, but it's actually something. Do you know what that is? Any guess what it's outputting here? It's outputting the memory address of where that node is stored. If you may recall in the last unit we talked about memory and I had that animation of mailboxes. This is the actual computer memory address of where the node is stored. Because when it goes to the superclass, what is the superclass of node? Object, right. So it's calling the toString method of object. Well, that's not useful. What we actually wanted to output was not the superclass, but the data. Oops. And depending on what the data is, it will look for a toString method. So for example, if we made our nodes hold the person class that we made in the last unit, it would look for a toString method in the person class. We happen to write one. If we made the node class hold huskies, it would look for a we happen to write one. If it can't find one, it goes back to the object class and just outputs memory addresses. Now, in some of the built-in classes, like the one we use, string, its toString method will do what you expect it to do. It's just going to output the string itself. So now, by changing the word super to data, we crash. But there's a reason for that. Which one of these nodes do you think is causing the crash? Which one can't it output as a string? Any ideas? Okay, so here, look them over. There's 4 nodes here. And if I said to you, tell me what the string version of N4 is, you'd say D. If I said, tell me what the string version of this one is, you'd say C. Which one is a problem? 1, because there is no data in there. It's a null. When it tries to turn null into a string, that's when it crashed. And you can actually see that right here. If I click on this, node toString, it's saying right here, when I try to turn the data into a string, I can't because it's a null. So why don't we add a little if statement in there? If, this is in our toString method in node, if data equals null, let's just return the word null. Okay? So if the data is a null, return the word null. Otherwise, take the data, turn it into a string, and return that. That should avoid the crash. Let's see. Let's see if that avoids the crash. Oh, my windows are all screwed up. Let me just reset my windows here. Let's try that again. And there it is. So notice now that the first node does not cause a crash because the null comes out. All right, so to do the toString method, we replace the word super with data. Okay? It's actually the data that's being turned into a string. However, in the case of our default constructor, the data will be a null. And we don't want that to try and turn a null into a string. So we're also going to add a little error check. If that data equals null, we'll return something else. We'll return the word null. Okay? Otherwise, we'll turn the data into a string. So that little error check right there will just prevent it from crashing when we create a default node that has data set to null. Now, for equals, we are really not checking the object itself, the node. What we're checking is inside the node, the data. So we're saying this.data, but we also need to check the data of the other object. The problem is this object is not a node, so we don't know if it has data in it. So what we're going to do is create a node. Node equals, and then that node is the thing that we'll be checking the data for down here. But how do we make a node? Well, we actually can cast, if you remember casting, the object into a node object. So by casting it into a node, now it can pull out the data and compare it to this. That completes our equals method. For the clone method, right now it is not deep, it is shallow. It's returning just a reference to the object itself. So to make it deeper, we need to create another node and return that node. And when we create it, we create a new node, and we can use our third constructor up here to set the data next and previous, but we want them to be copies. So we're going to say this.data, this.next, and this.previous, so that it makes an exact copy of the other node. One last thing is we can also reduce these 2 lines of code to 1 line by doing this. So we can actually create the node at the time we return it by creating what's called an anonymous object. So that object is just made right at the moment we return it, because that's the only part of the piece of spot where we actually need it to be created. All right, everybody. So now that the node class is finished, my advice is, I think you should take the time to comment all your methods here. Now, I wouldn't say that for a testing class like our collections test. Who cares if you comment this? It's just for testing. But if you guys think ahead, it's possible that you will be using this code we're writing now if you study computer science in the future. Because I guarantee you're going to be studying linked lists. And chances are you might even be using some of this code to hand in for an assignment in the future beyond my course. And wouldn't it be nice if when you went to do that assignment, you already had a class called Node that was already commented really well, and that would require no work on your part whatsoever? So I am recommending that you do take a little bit of time to comment some of your methods. Let's do a little of that together now. So for example, let's comment our final constructor, /** enter. Okay? So let's comment this particular constructor. So let's say that this is a constructor, sets class data. That's what it does. Data is the generic data type stored. Okay. Next is a reference to the next node. Okay. And obviously previous would be basically the same comments, except I'll change the word next to previous right there. So that didn't take too long to comment. Okay? So there would be my comment for that particular constructor. And again, because of the way we set up our constructors, the way I'd comment the other ones would be basically the same. I would just take that comment, pop it on this one, and just delete that thing. So now it's just that, right? And then I'd do that again. I'd take that comment, pop it onto this one, and delete that one. And then I would do the same thing again. Copy, paste, get rid of that. And with the final one, I might add the word default to the front of it, because that's the default constructor. But see, that didn't take that long, and you'll be glad you did, right? That, again, and you can see this from NetBeans as well. Now in NetBeans, when you bring up something like the navigator, and you look at your methods here, and you mouse over them, like I mouse over each of these methods, I'm getting my Java documentation provided to me here. Okay, again, I wouldn't recommend that with every class you write, but in ones you know you're going to be using over and over again, or possibly have a potential in the future, that might be worth your time. Okay, it might even be worth your time to, again, look at things like the normal little one that you put up here, right? So, you know, like clean up your name, for one, and actually write a description for what this node is. When we made it generic, it actually wants to add this to it. So you just say this is the generic data type, right? That's what T is. It's a generic data type. So again, that's just handy for your node. This will come in handy if you ever start using this class. You have all that built-in documentation there, built in. So I'm not going to do them all, but I just thought that would be something you guys could do on your time that might be worth your time. Okay? All right. So that completes our node class. It's done. We now will turn our attention to this for a long time. We're now going to work on our linked list class. Okay? Okay, so let's talk of the theory behind the linked list class. Okay, we saw it a little bit here. But there's going to be a bunch of methods here to do stuff in the linked list. We already talked a little bit about some of them. We want to add stuff to the linked list. We want to delete stuff from the linked list. Okay? Those are two features that you don't have with arrays. You can't add new spots to arrays or delete spots from arrays. All right, so in addition to adding and deleting, we also said that in order for us to use a linked list like an array, we have to loop through it, right? We can loop through arrays. So I'm going to use the word traverse, which again means to travel through the array. You could also use the word loop through, okay? So we want to be able to do that with arrays. To do that, in addition, like arrays, when we can go into a spot and change a spot, we need accessors and mutators, or setters and getters. We're going to need that, right? We're going to say, set this spot, get this spot. Okay? What else? What else is built into arrays that we take for granted? Well, if you think about looping, one thing we always do with looping with arrays is we use dot length to figure out how big it is. So it might be nice to remember how big our linked list is as well. So those are potential methods, and these two are a little more complicated than they look. Where do we add? Right, do we add to the front of the list, the back of the list, in the middle of the list? When we add in the middle, do we add in front of the thing or behind the thing? Same with deleting. If we have 20 versions of the letter A in our linked list, do we delete all of them? Do we delete the first one, the last one? So these are a little more complicated, but those will be the methods we're going to write in creating our linked list. But in addition to the methods, we're probably also going to need some properties, just like we always do. So properties of this linked list are actually a much shorter list. What do we need to remember about the list itself? Well, we need to know how many nodes are in it. So how many nodes? That would be a useful thing, because to me, that's actually connected to length, right? Length and how many nodes is the same thing. So that'll make our life easier there if we keep track of how many nodes are in the list. But let's look at a diagram of this linked list for a second to remember kind of how it works. We'll start with our node itself. Here's our node. Okay, we know our node holds data. I'm just going to put a D. And it has a connection to the next and a connection to the previous node. Okay, so I'm going to put prev here, and I'm going to put next here. That's our node, right? That's what a node will, that's what we'd have just finished working on, is all this stuff. Okay? So with that being our node, we are now defining a larger object called the linked list, which will contain a node, but it's going to contain multiples. So it's not just one node. It's going to be a node connected to another node, connected to another node, connected to another node, etc. Chaining them together into the list. But if we're going to travel through this thing, we know from any spot we can go forwards and backwards like a two-lane highway. We need an entry point. Where to enter the list. Now we could enter anywhere. We could enter anywhere along here. But I think it makes the most sense to enter this list at the first spot. From there, we can travel through to the end. Okay? Because unlike arrays, which have automatically index 0 and stuff like that, there are no indexes here. So we have to kind of create our own. But I'm going to actually propose we have two entry points. That's one. I'm going to suggest that we can have a second one. Clone. Isn't that weird that it says clone? Here. So we can also enter at the back of the list. Okay? It's kind of like as if there was an escalator, two-lane escalator in a department store. You can enter at the bottom of the escalator or the top and go either direction. That's kind of what we're talking about here. But we need names for these 2 points. We can't both call them enter. So there are lots of names that have traditionally been used for this. Some would call this the start and this the end. That's valid. I would absolutely say that's valid. Some call it the first spot and the last spot. That's also very valid. But I'm going to use words to describe these that I think is the ones you'll be using if you study computer science in university. The traditional names that I encountered more often was this is the head of the list, and this was the tail of the list. So I think we need these two things as properties of our linked list. So right here under properties, I'm going to say we need the head reference, like it's a reference to the head of the list, and the tail reference. Or you could use the word pointer. Pointer to the front of the list, or the head, pointer to the tail of the list. All right, so before we wrap today, let's just create the 3 properties. That's all we'll do. So up here, in our linked list class, and we're going to encapsulate them. They're going to be private, integer for the length. That's it for that one. So we're making it private so that you can't change it outside the class, which you can't do with arrays either, right? You can't take an array and say array.length equals 20 and expect it to change. It can't. But we're also going to make a private node for the head of the list and a private node for the tail of the list. And that is where we'll stop.